Hi guys, let's talk about the different shapes that we have for VESPR this year. So the first thing that you want to do when you draw your Lewis dot structure is you want to count how many areas of electrons are around your central atom. And so that's this column right here. From that, you basically come up with angles, you come up with the hybrid, you come up with the electron geometry. And then the second thing, after you figure all that out, is you see how many of those areas of electrons are actually bonded and how many are lone pairs. If there are no lone pairs, they're all bonded, that means that the electron geometry and the molecular geometry is the same because the shape that the electrons make is the same shape as the bonds make, since all the electrons are in bonds. And from there you can come up with this shape. It's going to be the same as the electron geometry. If you do have lone pairs, then what you do is you draw your central atom, and then you see how many bonds there are at those angles that you had already determined, and that will give you what the shape is. So let's start with two areas of electrons. So right here I have my central atom, and I have two areas of electrons. The farthest two things can be separated from each other, because remember those electrons repel each other, is 180 degrees. And so the bond angle that I have, the angle between this bond and this bond, is 180 degrees. And so if I have two areas of electrons, I have 180 degrees. The shape of the electrons is linear. In this case, the shape of the molecule is also linear because I don't have any lone pairs. And the hybrid is going to be sp, because if I have two areas of electrons, that means I need two orbitals to mix together, one s and one p, so it's an sp hybrid. And an example of that is BeF2. So if this was beryllium and those were two are fluorines. And if it is BeF2, this would be nonpolar. But let's say this is beryllium, this is fluorine, and let's say this is hydrogen, then it would be polar. Right, so the shape does not necessarily tell you whether it's polar or not. You have to look at what is bonded. If it's asymmetric, not symmetric, then it's polar. If it is symmetric, then it's not polar. So if it's symmetric like this one where both of them are fluorines, then it's non-polar. But if one of them is different than the other, then it is polar. Just for fun, if I were to remove one of these, so I have two areas of electrons, right? But I only have one bond. What shape would that make? Still linear, right? So whenever you have two atoms bonded together, no matter what, how many total areas of electrons or anything else, if there's only two atoms bonded together, they're going to make a line. So it's going to be linear. Okay, now let's look at three areas of electrons. So if I have three areas of electrons, the farthest they can be from each other, I put one up, one, all would be in the same plane here. Sorry, my molecule's kind of... So this would be, the bond angles would be 120 degrees apart. And since I have three areas of electrons, I determined that that's sp2 hybridization. And then if I look at the shape of my electrons, since they are 120 degrees apart, this is called trigonal planar. Trigonal because it's base 3, like a triangle. Planar because it's in one plane, right? It's not really... It's more like a 2D shape as opposed to a 3D shape, kind of. It's all in one plane. Because all of my electrons are in bonds, that means that my electron geometry and molecular geometry are going to be the same. And so my molecule is also a trigonal plane. Now, what if I remove one of these bonds? So I have three areas of electrons, but only two bonds. Then if I remove this, it's going to look like this. So I still have three areas of electrons. I have my lone pair here, if you can see it. So three areas of electrons, and so my angles are still going to be 120 because the electrons, whether in lone pairs or in bonds, repel each other. So the angle is still 120. The hybrid is still sp2 because I have three areas of electrons, three orbitals to mix. And the shape that the electrons make, it's still trigonal planar, but the shape that the molecule makes, that the bond makes, is different, right? So if I were to draw my central atom and then two bonds coming out at 120, then it's going to look like this, which is a bent or an angular shape. Okay, just for fun, what if I remove one of these bonds? So now I have 3 areas of electrons, but only 1 bond. And it's going to be linear, right? The shape of the electron is still trigonal planar, but the shape of the molecule is linear. Just looks like a line. What are the bond angles? No bond angles, right? There's no 2 bonds to make an angle, so no bond angles in this case. Okay, let's look at 4 areas of electrons. So if you have 4 areas of electrons, then you put them as far away from each other as possible. And so it looks like this. And the bond angle here is 109.5 degrees, just a little bit over 90 degrees. If you look at the hybridization, it's going to be an sp3 because you have 4 areas of electrons. So 4 orbitals need to mix, 1s and 3 p's to make 4 altogether. And the shape that this makes is called tetrahedral. Tetra means 4, like Tetris. And so hedral means faces, so it has 4 faces. So 1, 2, 3, and 4. 4 faces, tetrahedral. Now what if I take one of these out and put a lone pair instead? So it would look like this. Sorry, my lone pair is supposed to be right there, but it came off. So 4 areas of electrons still. So my bond angle is still 109.5 or close to it. Remember we said in our notes in the previous video that it's a little bit less than 109.5 because a lone pair pushes a little bit more. So it makes this angle smaller. But for the AP exam, just go with 109.5. So we'll say it's 109.5. The hybrid is still sp3. The shape of the electrons, the shape that the electrons make is still a tetrahedral, but the shape of the molecule is different, right? So I have my central atom, and I only have 3 things that are 109.5 degrees apart from each other. So this shape is called Trigonal Pyramidal. The reason is trigonal because it's base 3, 1, 2, 3, but it looks like a pyramid versus trigonal planar. So pyramidal and planar. Planar, it's in one plane, it's flat, versus pyramidal, it looks like a 3D pyramid. They're both base 3, but this is planar and this is pyramidal, because that's in one plane, so planar, and this is a pyramid, because they're squished together, right? Now, why is that? Because this has only 3 areas of electrons. 3 things can be 120 degrees apart, versus this has 4 areas of electrons. Remember, there's a lone pair on top here that's pushing those 3 down. They can't be flat like this. And so trigonal planar versus trigonal pyramidal. Okay, what if I remove another bond here? So I have 4 areas of electrons, but only 2 bonds. So it would look like this. So I have 2 sets of lone pairs, and then I have 2 bonds. Still 109 degrees. Again, it's in reality, it's just slightly less than that, but we're going to say 109.5 for the AP exam. Still sp3 hybrid. The shape that the electrons make is still a tetrahedral if you look at just the shape of the electrons, but the shape of the molecule is different. This, if you draw your central atom, and 2 things coming out at 109.5, that looks like a bent or an angular. Now notice we had a bent or an angular up here, so what's the difference between this one versus this one? Well, they're the same shape, but there's a different number of areas of electrons. So here's my angular that's on top with just 3 areas of electrons, so the angle is 120, versus this one has 4 areas of electrons, so the angle is 109.5. So this just has a larger angle because you only have 3 areas of electrons, so they're able to separate a little bit more. This one has 4 areas of electrons, so they're squished a little bit more together because 4 things are pushing each other. So 120 degrees versus 109.5 degrees. Okay, what if you have 5 areas of electrons? So here's what it would look like. So you have 1 up, 1 down, and then the other 3 make kind of like a peace sign. They're in the same plane and make a peace sign. So one up, one down, and then the other three are in the same plane, 120 degrees apart. So the angles here, we have two sets of angles, excuse me. We have 90 degrees right here. All of these are 90 degrees. And then we also have 120 degrees. So two sets of angles for this one. The hybrid, you do not need to know that for the AP exam. The shape that this makes is Trigonal Bipyramidal. So let's think about this. So trigonal, we said that means base 3. So if you look at this, there's my base 3. Bipyramidal, bi means 2, pyramidal means pyramid. So you have two pyramids here. You have, can you see? So ignore the bottom part, ignore this part. Do you see the pyramid that's on top right here? And now ignore the top part. Do you see the upside down pyramid that's down here? So two pyramids, one up and one down, and they're both base 3, so trigonal bipyramidal. Now let's say I take one of these away. So if I took one of these away from here, this is what it looks like. So there's my 5 areas of electrons, 1, 2, and then the 3 that are 120 degrees apart. But I took one of these bonds and put a lone pair instead. So this is what it looks like. So my bond angles are still the same, right? I still have 90 degrees, and then I have 120 degrees. So still the same angles. The shape that the electrons make is still a trigonal bipyramidal, just the electrons themselves. But if you look at the shape of the molecule, does this remind you of anything? Looks like a seesaw, right? Maybe like this. Does that look like a seesaw? So that's the name of it. It's not very scientific, but it is called a seesaw here. Okay, now what if I remove another one of these? So I still have 5 areas of electrons, but now I only have 3 bonds. So there it is. So 5 areas of electrons, 1 up, 1 down, and then 3 that are 120 degrees apart. Let's see, 1, 2, 3 there in the middle. So my bond angles now are just 90 degrees, right? I don't have any more of the 120s because I don't have any right here to make the 120 with it. So the bond angles here are slightly different. And what shape does this make? Well, the electrons themselves make the shape of a trigonal bipyramidal, but just the bonds make a shape of a T. And so it's called T-shaped. Okay, but if I remove another one, what's it going to look like? So I have 5 areas of electrons, but I remove 3 of the bonds. So I have 1 up, 1 down, and then my 3 lone pairs are kind of like 120 apart. Well, my bond angle here is a little bit different, even though I have 5 areas of electrons. But because I don't have any of the middle ones, the bond angle here is 180. So watch out, this is a tricky one. And what shape does that make? It's linear, right? Now another thing to watch out for, so this is XEF2 as an example, right? Is this polar or nonpolar if it was XEF2? So if this was xenon and these are 2 fluorines, is that polar or nonpolar? That would be nonpolar. It's symmetric, right? The fluorine would be pulling the electrons here, the other fluorine would be pulling the electrons here with the same amount of strength, cancel each other out. This would be nonpolar. We have not seen a shape last year where it had lone pairs and it was nonpolar. This is it. And so watch out, because lone pairs have nothing to do with whether it's polar or not. It's whether it's symmetrical or asymmetrical. And so a lot of students think, oh, I have a lone pair, it's going to be asymmetrical. That's not always true. You can see here, the shape is symmetrical even though it has lone pairs. So it has nothing to do with the lone pairs. What it has to do with is the electronegativity of the different atoms and how much they're pulling each other and whether they're canceling each other out or not. Now, if this was fluorine and this was chlorine, for example, then yes, it would be polar. But if they were both the same, then it would not be polar. Just for fun, let's say I remove this. So I have 5 areas of electrons, but only 1 bond. What shape would that make? That would be linear. No bond angles, because I don't have another bond to make an angle with. Okay, 6 areas of electrons. For some reason, this was one of people's favorite last year. So with 6 areas of electrons, I have 1 up, 1 down, and then the other 4 make like a plus sign. So no matter how you look at it, it looks like all the angles are 90 degrees apart. So my bond angles here are 90 degrees. For the hybrid, again, you don't need to remember what the hybrid is after sp3. For the shape, this is called an octahedral. It's also known as a square bipyramidal. I should have written that down here, but it's square bipyramidal. So let's think about those two names. Octahedral, oct means 8, hedral means it has 8, like the 8 faces. So here are the 8 faces. Look at the top, 1, 2, 3, 4, and then the bottom, 5, 6, 7, 8. So 8 faces, octahedral or octahedron. The other name is square bipyramidal. So like this one, but with a bi here, square bipyramidal. What does that mean? Bipyramidal, that means I have 2 pyramids. Let's see if you can find them. So there's the top, ignore the bottom, there's the top pyramid right here. And now ignore the top. So ignore this part, there's the upside down pyramid right here. So 2 pyramids, bipyramidal, but it's base 4, not base 3. So instead of trigonal bipyramidal, it is square bipyramidal. That means 2 pyramids that are base 4. Square bipyramidal or octahedral. Now let's say you remove one of these. 6 areas of electrons, but only 5 bonds. What would it look like? Like this. So remember, we used to have 1 up, 1 down, and then 4 that are like a plus sign. Well, I removed the one that's up, and I put a lone pair instead. So this is what it looks like. My bond angle is still 90 degrees apart. And my electrons still make the shape of an octahedral or a square bipyramidal. But what shape does just my molecule make? Just the bonds. Well, remember it used to be square bipyramidal? We removed the bottom pyramid, right? So now you just have the top pyramid. So it's just square pyramidal as opposed to bipyramidal. So just 1 pyramid that's a base 4. What if I remove another one? What shape does that make? So here it is. My up and down ones are now lone pairs. And I still have my 4 that are in the middle. So 4 areas of electrons still 90 degrees apart. The shape of the electrons is still octahedral or square bipyramidal if you prefer. But the shape of my bonds, square planar. Why is it square planar? Square because it's base 4. Planar because it's in the plane. It's flat. Just remember trigonal planar, right? Square planar. They're both flat. This is 3. This is 4. So trigonal planar, square planar. What if I removed another one just for fun? It would be a T-shaped, right? If I removed another one, linear. But you don't need to know those. You only need to know the shapes that are on your screen here. Okay, new is 7 areas of electrons. So let's look at 7 areas of electrons. Here it is. So you got 1 up, 1 down, and then you have 5 that are in the plane. Kind of looks like a Ferris wheel, right? 1 up, 1 down, and then 5 that are in the plane. So let's look at the bond angles. We still have the 90-degree angles here. Then these are 72 degrees apart, so 90 and 72. The shape of this is called a Pentagonal Bipyramidal. So bipyramidal, again, 2 pyramids. Do you see the top pyramid here? And then you see the bottom pyramid here. But this time, it's a base 5. So pentagonal, base 5, bipyramidal because we have two pyramids. What if I remove one of these? Here it is. So remember it was one up, one down, and then 5 in the plane. So I removed the top one and put a lone pair there. So what shape is this? Well, remember when we had one down here, we had two pyramids that are base 5. So it was Pentagonal Bipyramidal. We removed one of these pyramids, so now it's Pentagonal Pyramidal. Only one pyramid that's base 5. Pentagonal Pyramidal. Okay? Just for fun, you don't need to know this shape, but what if I remove this one? Then it's going to be pentagonal planar, right? It's going to be 5 in the plane if I remove that bottom one. All right, so lots of different shapes. A bunch of them are new this year, but hopefully they all kind of make sense. So draw your Lewis dot structure first, count how many areas of electrons are around you. From there, you can determine the bond angles and the hybridization, the electron geometry, and then from there, come up with the molecular geometry. Bye, guys.